Thank you, and a very warm welcome to everyone. Thank you for joining my presentation about the i2Mine project and ROS. In the next 15 to 20 minutes, I'd like to talk about the intelligent mine of the future and how we get used to the robot operating system in this project. I will start with a short overview of our research institute, and then I will introduce you to the i2Mine and its goals. We use different industrial-grade sensors from 1D to 3D, of which some have already been used in ROS, and some of which haven't been used. The main part of my presentation should be about how we adopt our system we already developed to the usage with ROS. I will close with an outlook and about the upcoming demonstration phase with our industrial partners and about more upcoming projects in the future. I'm from Germany, from RWTH Aachen University, and our research institutes concentrate on mining and metallurgy machinery. Our staff in our institute is about 60 personnel, and it's led by Professor Nienhaus. The i2Mine project is a EU-funded project which aims to reduce the resource dependency of Europe from China or from the other countries in the world. There are still some geo-resources in the grounds of the European Union, and with the current technology, these cannot be get to the upper level. Our industrial and academic partners are all over Europe, and the funding is about 25 million over a period of 3 to 4 years. 25 million euros is about 33 million US dollars as of today. The vision of the i2Mine project is to transform the mining from a mining which has much impact on the upper level of the world. It should transform the mining into a low impact mining which has very low impact to the environment. It should also improve health and safety of the workers by using robot technology. Our part in this project is collision avoidance and navigation of heavy machinery under the ground. This differs a little bit from robots I know because the environmental conditions underground are much different to the environmental conditions overground. There's dust, there's debris, and it could be very hot. Sometimes you have explosive atmospheres, so you need to take care about electricity. The sensors we use are from 1D to 3D. 1D like odometry with encoders, 2D laser scanners, 2 from SICK, radar technology, which is first used in this project. It's the radar system for ranging, which is developed at our institute. And we use 3D sensors like 3D cameras and ultra-wideband radar for ranging. We have a dual-use IMU, which outperforms all low-cost IMUs. The concept for navigation of heavy machinery underground is the same concept as doing navigation overground. We have there's some errors. We have IMU, which records acceleration, and when integrating this acceleration 2 times, you should get orientation position if you are in a perfect world. We are not in a perfect world, so we have some disturbances from the outside, and we needed different sensors to support the navigation algorithm. These supporting sensors could be laser scanners and 3D cameras, which are mounted on the vehicle. As we use different kinds of industrial-grade sensors. Each sensor had a different proprietary interface and a different protocol, a different data rate, a different data format. And so the first task was to do a unified interface of all the sensors. As we are in an industrial environment, we discarded USB because it's unreliable, and we chose Ethernet, which is widely used in other commercial products and industrial products. We built kind of little boxes to interface all sensors to a unified Ethernet interface. And as you can see from the mechanical box, it is ruggedized for underground use. In these boxes, we collect all the data and put them on the TCP IP stream on the network. So any application in our research network can use the sensor data. It also reduces the real-time burden of the application, because you don't need to collect the data all the time. It is possible to, if your application is running very slow, to collect every 5th sample or just discard the rest of your samples. This is some embedded hardware. We are using STM32 processors and an embedded Linux for the Ethernet connection. One of our problems was, because we had different sensors from different manufacturers, each sensor has its own time base. So every sensor does the sampling at a given rate. For example, the IMU samples at 400 Hertz, the laser scanner at 100 Hertz. And there's no synchronization between these two sensors. So as we had a box for every sensor, we decided to have synchronized clocks between all the boxes, which are not always mounted at the same position. On a big machine underground, they could be like 5 meters away. So we used the precision time protocol to synchronize local clocks in all the boxes. And as soon as a sensor sends its data to the sensor box, the data is immediately time-stamped with the current time. The time precision is in the microsecond range, so even if the sensors are distributed widely around the vehicle, we always get every data sampled at the time when it was created by the sensor. There's no delays like if you have an application like ROS, it's not deterministic, and it may or may not sample your data or receive your data from the sensor when the sensor sends it. So far, this solution was developed without ROS. We did not know about ROS until 6 months ago, because it's not common in our field of research to use with automation technology. So we are quite new to the subject. This all worked very well. We got our data stream from all the sensors. We were able to develop our algorithms, like strap-down algorithms for the IMU, or visualization, or some measurements or comparison with different sensors. But we reached a boundary when we wanted to have to visualization and to store data. And this is where ROS came into account. We found out that ROS has a very good interface for visualization, ROS plugins, and it has a back files, which is very convenient to store data, and it's very convenient if you have a measurement campaign, which only happens twice a year for us, where you go underground with the machinery, take your sensor data, and then like to reuse the sensor data in your lab like 3 months later. The back file is very convenient for such a task. So our task was to ROSify all our sensors, and of course, if you go higher level tasks, we wanted to use already developed algorithms like the SLAM algorithm or the extended Kalman filter from ROS. So it was worth the effort to change our system from for our own system to a ROS system. But there was a dilemma because the standard ROS messages are already defined, like the IMU message, and not all our sensors exactly produce the kind of data the ROS messages include. For example, the IMU samples its temperature, and our measurement campaigns are very expensive. They only happen twice a year, and so we did not want to discard any of the data because it's quite expensive. So what we did is we created our own messages which include all the data the sensor provides, and to use all the ROS tools like ROS or the included filters. We used conversion nodes to transform our data to the data of ROS. At this point, we discard all the data we don't use at this point, but we did not discard it when recording the data in the field. To record the data, we built our own mobile robotic test platform, which is battery powered. It's about 800 kilos. It can be moved by a remote control, and all the sensors, like the IMU, the encoders, 2 laser scanners, the radar, and ultrasonic distance sensor are all mounted, and 2 infrared cameras are mounted on this platform. It's ruggedized, so we can move underground with no problems. On the left, I prepared some of the results. We used the ROS tools to visualize all the data collected by the 3D laser scanners, and the location which was generated by the odometry and by the SLAM algorithm. This is a lot too small, I'm sorry about that. This is our concept at the moment, using a large number of ROS nodes which collect all the data from sensors, convert them to the ROS messages, and then are fed into the algorithms like SLAM or EKF. On the right-hand side, there are the 3D and 2D maps generated by SLAM. This is an underground section with 2 tunnels joining in a point. And we used tools from the underground industry, from the mining industry, to verify that these plots are correct and that our SLAM algorithm is correct. As we are very new to ROS, there are some lessons we learned during the last 6 months. I need to admit that we got off the ground very well with ROS. It was what was difficult in the beginning because it was so much and we did not really know where to start. But then it was very easy to get the first data displayed in ROS, and it even was possible to extend ROS in the way we wanted. As I mentioned, we created our own messages, not to discard any of the message data from our sensors, and it was a bad idea to change the message formats during the development cycle, because then all the algorithms on all the nodes did not work anymore because the data format changed. So we needed Git to revert some of the changes in our nodes and compile again. A good idea was, because there were several people working on the project and we had different nodes in the project, to use a Git repository for each node. So it was easier for the students who worked on the project that everyone has his or her node and his or her Git repository. So it was easier to commit and to do to pull the new changes from the server. You did not have to merge or anything else. And we used Git slave to maintain a large directory structure of all the nodes in the Catkin workspace. I would advise everyone to use a visual camera system all the time when you record data, because sometimes it was not possible for us to really understand what we did with the rover, and it would have been quite easier if we had a data stream from the visual camera during the test run. I said most of the things worked out of the box quite easily. There were some problems, like the camera. We had an Ethernet-based camera, and it should be supported by ROS, but this just didn't work. Some of the nodes crashed sometimes. We generated our own messages, and there's some problems with the dependencies. So if you create new messages, which are in a different node than another, it was difficult to make sure that Cat can generate the messages before it compiles your node. And the version of PCL included in ROS did not include all drivers for all cameras, so we had to recompile the PCL for ROS to include all camera drivers. I'd like to give a short outlook of what is coming next. Next month, the demonstration phase is about to start, where we will go on another measurement campaign, take our sensors and mount them on a machinery of our industrial partners. It will take about 1 year, and then we will hopefully have new results. There are 2 more projects in the pipeline, one nationally funded from Germany, and another project in the Horizon 2020 program of the EU. In both projects, we are quite sure that we will keep on using ROS, because it was very helpful to do all the stuff you don't want to do, like storing data, visualize data, and we were able to concentrate on algorithm and stuff. Okay, I like to close my presentation with a very big thank you for all your work you have done in ROS, and of course for your attention for my presentation. So if you have any questions, please feel free to contact me at any time. Thank you.
Questions? So you mentioned a few of the problems, like particularly the one about cat can generate messages and make sure the messages got generated before they use them in front of them. I was wondering, like, when you ran into that problem, like, what routes did you take to try to figure out? Did you like get the ROS answers, or did you try to stick with just like the documentation?
No, we just found a way to. Oh, the question was, what did we do when we encountered the problems with the Catkin and the generated messages? Well, we found a solution just by doing some of the Catkin commands manually, like the generate message CPP stuff, doing this 2 or 3 times, and then it worked out fine. So we did not use ROS answers yet.
Okay, so I guess my point was that's come up a few times, and obviously the best thing would be for people not to run into it. That particular problem hasn't been a conceptual issue with it, but it's for us to fix it automatically. But I was just curious if you had trouble finding a solution, because we're trying to make like ROS answers and stuff.
Other questions?
Which SLAM algorithm are you using for the lines?
The SLAM algorithm from the navigation stack.
Oh, so G mapping?
The G mapping, yes.
That works okay, like going up and like is the line flat, or is it?
It's relatively flat. Yeah, that's because the machinery is big and it doesn't like to go that way.
Okay, one more question. I've got one.
Okay.
So you're doing this research. How targeted is it toward actually deployment?
Your question was how far is it from deployment? I would say very far, because we started with evaluating sensors and if sensors are suitable for underground navigation. And the outcome of the project, I think, should be to show that it is possible to do navigation underground with the sensors we selected, with the industrial grade sensors. And mining industry has, I would say, a conservative development cycle. So it would take another 5 or 10 years until you see products with ROS in the mining industry, in Europe at least. I read about something in Australia or in the US, might be different, but in Europe it would take another time. Thank you.
Thank you.